20. We're going to talk a little bit about hash tables today. This is Judy.
And this is DJ, one of your TAs.
So, it's come to my attention that I may have used the word key in the hash table and associative array materials kind of often. This has come to my attention by the use of this word cloud in front of you, where key and keys are two of the largest numbers. So, given that this may not be completely clear what all this is about, we thought we'd make a short video kind of trying to disambiguate what some of these terms mean and how hash tables are used to get you started on the concepts. Question the first. What is a hash table for? So a hash table is really just an array in implementation. What you use it for is when you have some kind of data for which, given one part of the data, you might need to find some other part of the data.
Wait, so does that mean that we have two different sets of data or two different types of data, or a data that has two aspects to it?
It typically means that you have a struct of data that has two or more aspects in each struct. So it would be like maybe a student with a name and a student number and some classes they're enrolled in and an email address. And all of those pieces of data could go into one struct. And maybe we know the student number of all the students and we want to know their email address. We could use a hash table to store the whole pile of data and use the student number to quickly find the email address given a student number.
Okay, so we're using one bit of known data to find a bit of unknown data related to that known bit of data.
Correct. And a hash table is always about data that are related to one another in some way. Typically, those data are all represented in a struct where all the little pieces of data are in one struct. So where does this key thing fit in? The key is the piece of the data that you're using to find the rest of it. It isn't really separate data. It's still part of the whole record, but it's sometimes useful to know what it is and to keep it out. So in our implementations that we're doing for this class, we're actually storing the key, or we're storing the key with the data, but I've got you using it as a separate entity as well, just so that you don't have to muck around with quite so many void pointer casts and that sort of stuff.
So in the student name and student number analogy, the student number is the key or the student name is the key?
Probably the student number. The beautiful thing about a key is it can be anything. Ideally something that uniquely identifies that set of data that goes together. So in this example, a student number would be a better choice than a student name. You've got a fairly high likelihood of having 3 or 4 Jane Smiths in your class, but everyone has a different student number. So, the way this works is you build an array, and you've got this data that is related one to another. The materials in the course link have 2 different sections, one on associative array and one on hash tables. We're going to talk about the associative array things. They're almost identical. The associative array section is just to get you thinking about this kind of data where you have some kind of a value that lets you find the other piece of data. So in the associative array materials, you'll see this table. And the table has these keys, 1, 2, 3, 4, 5, 6, 7, and the dwarves from Snow White. The thing that's not clear in this example is that why is this key associated with sleepy, other than the barking dog? I'm just gonna leave her barking.
That's fine. That's fine. There's cameo appearance by the barking dog.
So that could have been made clearer in the materials. Right now, assume that for whatever reason, Sleepy is dwarf number 1, and Doc is dwarf number 2, and Grumpy is dwarf number 3. And if we look up 2, we expect to find Doc. And if we look up 4, we expect to find Happy. You can say that they're employee ID numbers, and for whatever reason, they are mapped to 1, 2, 3, 4, 5, 6, 7.
So, just for clarification, in this associative array, the key is the position in the array?
And that's the key difference between associative arrays and hash tables. In an associative array, the key is the position in the array.
So just by simply knowing what the key is, you know what the position in the array is that holds the information you're looking for.
Exactly.
Okay.
And the array might actually be holding the value, sleepy, or the array might be holding a pointer to an entire struct that has sleepy and a bunch of other values in it.
Right. So we're working with arrays that could ideally be abstracted out to hold a struct of our own design.
Absolutely.
To carry the data across.
Right. But in associative array, your key tells you what position it's in. And in this implementation, which is an actual array implementation, if you don't have a value for position 5, you leave it empty, because we don't expect to look up anything for 5 and get a value.
And by empty, you mean like non-initialized?
Usually what you do is you put what's called a sentinel value in it. And that's what this empty word is. So in your implementation, you've just defined some special value that says, hi, I'm empty. The danger of leaving them uninitialized is that the compiler may leave extra stuff in memory that then looks like it's an actual value and throws your program off.
Okay, so empty is a predefined placeholder.
Yes.
Gotcha.
Yeah. All right, so that's the first bits of associative arrays. The second part of associative arrays is the linked list implementation of an associative array. And this is exactly the same data. And this could all have been one gigantic struct, but I had a struct for the data because I just did my linked list. Here's my data, and then it has a pointer off to the rest of the record. And so we have key 1, key 2, key 3, key 5, key 6, and key 0. I lied. It's not exactly the same data. Notice they're not in order because they don't really have to be. We're still looking up 6 and getting dopey and looking up 3 and getting happy. And so, again, just assume these are their employee ID numbers or something. But with a list implementation, you don't have to have them in order and you don't have empty spaces. If something's in the associative array, it's there because it has a value.
Right. But if we were trying to find something in this, we couldn't do list at position. You have to somehow traverse the list to get to it.
Right. And so an associative array is useful if you don't have a huge amount of data, but it has all the same problems that any list search does, where it's an order n operation, because you're probably going to have to, worst case, start at the beginning and go to the end.
Right.
So not the best choice for a large, like a really big pile of data, but for sort of a quick and dirty data structure to store some stuff in a relatively small amount of space and a really low amount of implementation work, not a terrible choice. Associative arrays lead us into an understanding of hash tables. So the hash table is almost exactly the same thing. Thank you, CourseLink. The difference between a hash table, do Do I have another picture? I don't. The difference between a hash table and an associative array, there's my other picture, is that the table position is not part of the record of data. So in this example, again, let's assume that my dwarves now have different, maybe this is their age, but they have different numbers associated with them. So 143 for whatever reason goes with Doc, and 45 for whatever reason goes with Grumpy, and 98 goes with Half-P, and so on. What we do with the hash table is, rather than saying, okay, we're going to put Doc in position 143, we write a special function that turns these keys into a table position.
So what we're taking is some aspect of the data, and in this situation we're saying their age. For whatever reason, Bashful is 199 years old and Grumpy is 45 years old. And sending it through a function that returns us the table position?
Correct.
Okay.
And that function is called a hash function. And it always, so the hash function can be anything that anyone writes. And for whatever reason, however you write it, it always has to return the same table position for the same number. So what we do is we run 143 through our hash function. It says 0. We put Doc and all of Doc's related data in position 0.
And that would normally be encapsulated in a struct.
Would normally be encapsulated in a struct and stored as a void pointer in the table.
Okay.
Just like we were storing them in our lists.
So we have an array of void pointers. We hash the age of Doc. It tells us to go to position 0. We put the struct that is Doc and his age at position 0.
Correct.
And it has to be the true definition of a function and not a relation, because we need to be able to go forwards and backwards.
Right. So we need to later then be able to say, oh, where's Doc? Hash 143, and then go back and get him.
Right. So the function has to always give us the same number given the same seeded information.
Given the same input, it always gives us the same number. And so we go through and we put all the rest of them here. Now, the difference with the hash table is that it sometimes will have two things in the same position. Maybe Bashful and Sleepy, who isn't shown here, both their ages hashed to 3. And we do that by just creating another linked list that kind of goes off of position 3.
So every struct should have a something pointing to the next thing that also is sharing that position?
That's the most common way of handling these kinds of collisions, yes.
Okay.
There are other ways of handling collisions, and they're all explained in the reference materials. But given that everyone already has a linked list implemented, using the linked list approach to collision resolution makes the most sense.
Okay.
So down at the bottom of the reference materials, way at the bottom.
Look down. Look way down. None of them will get
Nobody
that reference.
gets that reference.
No one gets that reference. Hashtag look up the friendly giant.
So this is what it might look like if we were actually had Sleepy colliding with Grumpy. We would have the array, and here in this example, 98 has hashed to position 1, and 123 is also hashed to position 1. And so Grumpy is originally the void pointer in position 1, and then Sleepy gets added in. So in implementation, this probably ends up being that 98 and Grumpy are the void pointer, and this outside box is the node from your linked list. And so this is actually a node with a pointer down to 98 at Grumpy, and this is actually a node with a pointer down to 123 and Sleepy. There's a lot of pointers.
And again, just for clarification, we're saying for sake of argument, these numbers, these keys, are their ages
Yes.
already. Somehow
And Happy is now 653 years old.
Happy is now 653 years old. You
And
know,
Sneezy's 789.
they're doing great for their age. They're doing great for their age. Must have really awesome retirement benefits.
Exactly. So that's the basics of a hash table. And all this talk about keys is just the aspect of the data that you have selected to be able to create a table position with some kind of an algorithm and retrieve the table position with the same algorithm.
Okay.
That's the intro.
That's the intro.
Anything else we should tell them, DJ?
I think one of the important things to underline, in case it wasn't super obvious, is so far our keys have been all of numerical values. And you should keep doing that. We'll probably talk a little bit more about later on about what to do when you don't have a numerical bit of data to use as your key. But for now, when you're trying to understand hash tables, make sure that you're working with some set of data that has a numerical key, like the name, and student number, stuff like that.
Student name and student number and email address is a great set of data to use for your own testing purposes. You know how it works, you know lots about the data, and it's easy to generate.
Yeah.
All right, that's it for this one.